All right, welcome to Unit 2, Exploring Two-Variable Data. This is an extension to Topic 2.8, Least Squares Regression. And what we're going to do in this video is we're going to look at a problem where we cover all the big kind of ideas that we learned in 2.8 on least squares regression. All right, so here we go. Here is the problem. Windmills generate electricity by transferring energy from wind into turbine. A study was conducted to examine the relationship between the wind velocity, measured in miles per hour, and electricity production, measured in amps, for one windmill. The amount of electricity was measured over several different wind speeds, ranging from 10 miles per hour to 40 miles per hour. The scatter plot looked mostly linear, that's awesome, and a regression line was formed to predict electricity output from wind speed. A computer output table of the regression is below. All right, so what do we learn from everything that we just read? Well, it says that we're trying to predict electricity, so that becomes our y, based on wind speeds, that's our x. Now, they also told us that our data came from wind speeds of 10 to 40 miles per hour, so trying to make any kind of predictions above 40 or below 10 would be extrapolation and not recommended. Anything between 10 and 40 would be good to go. We could be able to use our regression. All right, now this is a computer output table below that we discussed. This is simply a fancy way for me to give you the equation you need, which is y hat equals a plus bx. Now, like I mentioned, you're never going to need p, t, or the se. And also, sometimes you'll see what's called r squared adjusted. We're never, ever going to use that. Don't worry about what that is. All right, so the cool thing is, right next to the word constant or intercept is your a value, alphabetical order. Directly underneath that is your slope. So you literally cannot mess up the coefficients, a and then b. All right, so all we have to do now is actually write the equation. So that's going to be y hat equals 0.137 plus 0.24 times x. Now, oftentimes you will be asked to define the variables. The variables are x and y, hat. So the 0.137 and the 0.24 are coefficients, right? That's the slope and the y-intercept. Those are not variables. They're now numbers that represent something for this problem. The variables x, wind speed, and y hat, the predicted electricity output in amps. All right, so make sure that you understand all that, right? Like I just went over all that, but make sure that's pretty clear. So the equation is going to be y hat equals 0.137 plus 0.24 times x. Again, you cannot mess that up. A and then B in the table there, alphabetical order. And then again, define the variables. So make sure you tell me x is the wind speed. I get a lot of kids that will try to talk about slope and y-intercept. Those are not variables, those are coefficients. And then again, make sure we have units here, miles per hour. Sorry, I'm being a little messy. I'll try to be nicer. The y hat is the predicted electricity. And they said that was measured in amps. All right, so now the next thing that we want to do that's very, very common is to interpret the slope. All right, so let's talk about the slope. All right, the slope is b, and that is 0.24, and I recommend making it a fraction. The denominator is always 1, and the actual slope value is your y. So this is what we predict y to change by for every 1 more mile per hour of wind. Now we just got to write that real nice, right? So let's go ahead and actually start typing this in, because I know my handwriting is a little bit messy, so I'm actually going to type this in real nice. That way it's very, very clear. All right, so if I'm interpreting the slope, I'm going to say the slope of 0.24, and look, I already have a typo there. The slope of 0.24 tells me that for each additional 1 mile per hour of wind, it is predicted that the electricity produced increases, because it's positive, by 0.24 amps. So that's a really nice way of saying it, but essentially we're just simply saying, hey, for every 1 more mile per hour of wind, that hits this windmill, we are predicted, make sure you have that word predicted because there's no guarantees here, that we're going to get 0.24 more amps of electricity. Obviously, you could write this sentence several different ways and still get it correct, but it has to have that flow, that for every 1 more mile per hour of wind, we're predicted to get 0.24 more amps of electricity. Or you could write it backwards if you want. You could say it is predicted that the electricity will increase by 0.24 amps, comma, for each 1 more mile per hour of wind that hits the windmill. But you got to make sure you understand that interpretation. All right, up next is the y-intercept. Remember, a y-intercept is what we predict y to be when x is 0. So we would say the y-intercept of 0.137 tells me that, oh, another typo, I'm bad at typing, tells me that if we had 0 miles per hour of wind, we are predicted to still get 0.137 amps of electricity. Electricity. Bad typer. All right, now that might be extrapolation because remember our wind speeds were gotten from 10 to 40 miles per hour. So making a prediction for 0 would be extrapolation. I'm still going to write that sentence. I'm not wrong by writing that sentence. It just may, not 100% be accurate. But the 0.137 is my y-intercept. That doesn't change. It's not like I did something wrong there. It just sometimes, we talked about, sometimes it makes sense, sometimes it doesn't. But I cannot tell you how important it is that you know how to interpret slope and y-intercept. These questions will definitely be on any assessment you have covering linear regression models. All right, what else could I ask you? Well, I could ask you to discuss the reliability. So let's make sure you remember this from the video. Here we're going to look at S, the standard deviation of the residuals, and R squared. Let's start with R squared. R squared actually tells me how connected these two variables are. It is the percent of variation in the electricity that is actually explained by the variation in wind speeds. Now we just got to make sure we write that real nice. So first up, R squared is a percentage. So it's 87.3% of the variation. Yeah, I cannot spell today. Variation in electricity that is explained by the variation in wind speed. So it's this idea that when we look at our data, we have lots of different electricity in amps, we have lots of different wind speeds in miles per hour, and 87.3% of those different electricities is actually explained by the different wind speeds. So that's pretty strong, right? I mean, that's pretty good, right? All right, up next is S. S is the standard deviation of the residuals. Remember, the standard deviation of residuals, it's like an average of all of your residuals. So it says something like this. When we use our model to predict electricity from wind speed, I have a hard time spelling electricity today. So when we use our model to predict electricity from wind speed, we are typically off by about 0.237 amps. Now, I don't know a whole lot about electricity. I don't know a whole lot about turbines and amps, but that sounds pretty small, right? I mean, it sounds like if I'm only off by 0.237 amps of electricity, it doesn't sound like I'm off by that much. And that's a good thing, right? Now, remember, off could be a little above or a little bit below because standard deviation of the residuals is an average of all of your residuals. And some are going to be positive, some are going to be negative. So it's just an average distance away from the prediction. So this is actually pretty good. So in terms of reliability, I think that this line is actually very reliable. It has a very strong R squared that tells me that these two variables are definitely connected. Wind speed has an awful lot to do with turning that windmill and making electricity. And even when I use this model to try to predict the electricity, it's pretty good at making predictions. It's only off by 0.237 amps. All right, the last thing we're going to do is actually predict electricity for a wind speed of 18. Now, 18 does fall in my window of 10 to 40 miles per hour, so this should be pretty good. So the electricity is going to equal 0.137 plus 0.24 times 18. And I'm just going to go to my calculator right now and just type this in, 0.137. And again, this is showing my work, pretty easy. Plus 0.24 times 18, and I get 4.457 amps. So pretty easy to do there. So it is predicted that you will have 4.457 amps for 18 miles per hour. Now that is the predicted value, right? So pretty simple there. Hopefully that's not a problem at all. That's usually really easy and nobody really messes that up. But I will say that a lot of kids do mess up these interpretations of R squared and S. So please make sure you take the time to analyze how I'm doing it. And like I said, unfortunately or fortunately, it depends how you look at it, it's really just like a script. You have to follow the script to interpret these. All you have to do is fill in the explanatory and the response variable from this specific problem with units. And as long as you're good at doing that, it's really not that bad to interpret all of these values. All right, guys, so hopefully that was kind of like a quick example just to get you, a feeling for what's going to be asked of you on a test, because this is like a perfect test question right here. I give you this computer output table. I ask you about the model. I ask you about slope and y-intercept, and then I move it on and ask you about reliability. So this is a pretty good, indication of what you're going to see coming up on a test or quiz. All right, guys, that's it. Hopefully you learned something. See you in the next video.